Thank you so much, Daphne, for the invite and for giving me this opportunity to share with you some of the projects I've been working on in the causal inference field, and namely how we use or develop methods around marginal structure models to estimate the causal effects of continuous time treatments. So first, I'd like to thank my colleagues. These are mentors, collaborators, mentees, who all of them have been very instrumental to me during the times I work on these projects. So this is sort of introductory slides to folks who may not be very familiar with causal inference, but I see a lot of causal inference expertise in the audience, so maybe this is not necessary. But the potential outcomes are essentially the cornerstone of causal inference. So suppose we want to estimate, we want to estimate the causal effect of a binary treatment on some outcome y, right? So in the potential outcomes framework, the average treatment effect can be defined as a difference in the means of two sets of potential outcomes. So y1 here is the potential outcome that would have been observed had everyone in the population received the treatment. And y0 is similarly the potential outcome that would have been observed had no one in the population received the treatment. And then the randomized control trial is the typically the gold standard to estimate the causal effect, in which we would randomly allocate patients or units to receive either the treatment or placebo. The randomization would more or less make the two groups of units more or less similar in terms of their characteristics, so that a person's potential outcome to either treatment or placebo or control would not depend on which treatment group this person was assigned to, but simply depends on how the treatment works. So the potential outcome would be independent of the treatment assignment. And then in this case, we would just simply look at the difference in the observed outcome between the two groups, and that's the causal effect. But in many cases that I'll be talking about later, we cannot conduct RCT, so we have to rely on observational or non-experimental data to draw causal inference. So in this case, the potential outcome would not be independent of treatment assignment, because there might exist a confounder that is predictive of the outcome, such that the probability of receiving treatment depends on the covariates. So age might be such a confounder. For example, older patients are more likely to receive a treatment. And then, so in this case, the between group difference would not bear causal interpretation because it might be confounded by age. So then we have to rely on specialized causal inference methods to estimate the causal effect. And there are many methods out there, but today I'll be just focusing on the marginal structure models because it's relatively simple to implement and it has good statistical properties. And it's versatile enough to accommodate many complications associated with non-experimental data that I'll be talking about a little bit more later. So we can propose a marginal structure model that relates the potential outcome with the treatment assignment. So somehow I cannot show my mouse, so sorry, I just don't want to bring out my mouse pointer. I think it's okay. Okay, sorry. So, so we can propose a marginal structure model that relates YA to treatment assignment. And then, but in reality, we have to fit a model to the observed outcome to estimate the effect. So theta 1 here encodes the causal effect. But when you fit a model to the observed data, the coefficient beta 1 here only measures association, but not causation, because of the confounding reason that I just talked about. But we can get to causation by solving some weighted estimating equation, and with the weights being the inverse of the conditional probability of treatment assignment given some confounders. So this is so-called inverse probability weighting. It works because it removes confounding by X in the weighted pseudo population. So that's sort of how we can use marginal structure model in a relatively simple causal inference setting. But so causal inference techniques traditionally focus on time-fixed treatment assignment mechanisms. So units were assigned to receive certain treatments at baseline, for example. But then with increased availability of large-scale health-scale data sets, there is this increased demand for more refined causal inference techniques to evaluate more complex time-dependent, more complex treatment regimens, and time-dependent treatment can be such a case. So time-dependent treatment can be static or dynamic. Static meaning that the start or stop of the treatment could depend on the time. So for example, after the enrollment, start the treatment 2 weeks after the enrollment, 4 weeks after the enrollment. And dynamic meaning that start or stop of the treatment could depend on some covariates that is time varying, that also depends on time. So for example, blood pressure. Okay, blood pressure can be repeatedly measured, and the treatment decision could be made depending upon observing the changing values of blood pressure. So these are types of treatments that are time dependent. And in these cases, it is just infeasible to conduct randomized controlled trials because there are simply too many treatment time points to be compared. So we're gonna rely on specialized causal inference methods. And the next, I'm going to give you a few, actually 4, sort of motivating real world research questions that motivated us to develop methods around marginal structure models in order to solve these questions. So the first example is kind of a static continuous time treatment regimen. It's timing of HIV treatment or antiretroviral treatment, we call it ART, for patients who present with both TB and HIV. So for these patients, TB therapy is recommended to be initiated immediately after diagnosis. But during the TB treatment, when to start the HIV treatment or ART, that is a very important question because early initiation obviously can increase drug toxicity and risk of TB-associated immune reconstruction in inflammatory syndrome. But late initiation could also increase the risk for morbidity and mortality associated with AIDS. So the key question here is, what is the optimal timing of ART initiation? So that is time dependent and that's static. And the next example, more recent example, that's COVID-19 treatments. And these treatments patterns are actually very complex and that they could also depend on time. So this is actually a data example on a random patient drawn from our Mount Sinai COVID-19 registry. So for example, this person, after he or she was admitted to the hospital, this person was taking dexamethasone for a few days, right? At some point, in addition to dexamethasone, this person was taking another corticosteroids for some other days. And then at some later point, this person switched off corticosteroid and started taking another anti-inflammatory drug and medication for some other time during his hospital stay. So you can see that the 3 treatments are under consideration here, and the start and stop time of medications can be time dependent. So the next example is actually a dynamic treatment regimen, but also depends on time. So WHO guideline for the timing of ART initiation for adolescents, essentially kids, used to depend on the evolving value of CD4. So CD4 is a very important marker of immune function, immune system function. So this guideline takes the form of a treat when CD4 cell count drops below a threshold, say 350. So typical data is this person came in, had an initial measurement of CD4 at 500. Next visit, CD4 was down to 450, and the next visit down to 400, and the final visit down to 330, which is below the threshold. And then starting from this time onward, the person was starting to take ART medications. So this is an example of a dynamic treatment regimen. And the question is, what is the best threshold? What is the best Q? So the next example, this is also some ongoing project we're currently working on, and very similar to the previous example. It's initiation of antihypertensive treatment. So antihypertensive treatment, this is a blood pressure lowering treatment. So that this is depending on the evolving value of blood pressure. So the current guideline says treat when systolic blood pressure goes above 140, for example. Similarly, patient came in, had an initial measurement of 125, right? Next visit went up to 130. Next visit increased to 135, and the final visit reached 145, which was above the threshold. So from this time onward, the person was starting to take the antihypertensive treatment medications. And the question again is, what is the best threshold Q? And actually, this is an unsolved question, especially among the very young population and the frail old population. There's just a lack of direct evidence from the randomized control trial. So these are sort of four motivating real-world research questions that motivated us to develop methods in order to solve these questions. So then I think for the next part of my talk, I'll be focusing on the development of statistical methods to address these questions. So I think I'll be focusing on the first example. I'll be using the first example, the continuous time static regimen. And if the time permits, I'll also talk a little bit about the methods for the dynamic treatment regimen. Okay, so the key challenges for us to use the observational data to draw the causal inference about treatment timing is that there are a lot of complications. The immediate complication is, of course, the treatment was not randomly allocated. And then both exposure and outcome are time to events. So exposure is time to treatment. Outcome is time to death. And both are time to events, and both are subject to censoring. So people could leave the study, and that would lead to incomplete information on exposure or outcome or both. And then people, so the follow-up visits are also pretty irregular. So they come and go at irregular times. So the follow-up visits are not nicely aligned. So these are complications. So, and then these are sort of four patterns, censoring patterns we observe in the data. Our goal was to estimate the effect of A, treatment initiation time, on T. But we only have a small proportion of patients that have complete information on both A and T. A large amount of patients, they left the study. So their death times were censored. And then some patients died before they even had a chance of being treated. So their death times were censored by death. And then about 20% of patients, neither A nor T was observed for them. So both A and T were censored by C. So these are really incomplete information. And how do we properly use this incomplete information to draw valid causal effects of A on T. That's something we wanted to do for the project. Okay, so then our general solutions are to first formulate a flexible structural causal hazard model that can capture both the effects of timing and duration of the treatment. And then we can derive methods to generate consistent estimates of the model parameters under non-random treatment allocation and the 4 sensory patterns we observed in the data. And using these model parameter estimates, we can further generate the estimates of the functional causal relationship between treatment initiation timing and mortality. So some standard notation before I bring up the methods. So again, we have 3 time to events: treatment initiation, death, and sensory. And then we use T sub A to denote the death time associated with A. So T sub small a, that's the potential death time if treatment is initiated at A. We use T sub infinity to denote the death time if the treatment is initiated beyond some time point of our interest. So between T and C, death time and sensory time, there's a minimal observed time point, T star, and corresponding event indicator. Among these 3 time to events, there's a minimal observed event time, corresponding event indicator. We use L bar of T to denote the covariate history up to T, but not including T. Okay, so now with that notation defined, back to the 4 sensory patterns. In the first case, we observe both. So we have A, we know T of TA. Second case, T is censored by C. So we know A, and we know TA is greater than C. And third case, A is censored by T. So we know A is greater than TA. And the final case, both A and T are censored by C. So we know A is greater than C and TA is greater than C. Okay. So, and then we propose a structural causal proportional hazards model. And lambda A of T here is a hazard function for the potential death time T sub A. So patients start to follow the baseline reference hazard. Once the treatment is initiated at A, the instantaneous effect of treatment initiation is captured by this G1 function. And then at any time T, the effect of being on treatment is captured by this G2 function of duration, treatment duration. And then, the interaction between the treatment initiation and treatment duration is captured by the G3 function. So we left the model highly flexible. So the reference hazard was left unspecified. And also we'll use the smooth functions to estimate the 3G functions. Specifically, we could parameterize the 3G functions using the natural cubic splines. So we would rewriting the 3G functions in terms of the basis functions of the natural cubic splines, and as well as the parameter beta. So now the parameter beta captures the causal effect of ART initiation on mortality. So then now our next objective is to obtain a consistent estimate of the beta using observed data. And once we have that, we can plug that back in to obtain the 3 G functions to understand the relative contribution of timing versus duration and our interactions. And then we could also derive the causal dose response of initiation time versus mortality by deriving the counterfactual or potential survival curve from our structural model by relating survival function to the hazard function. And then we can further estimate the model-based optimal initiation time, say that would maximize the survival probability at a target measurement time, say 52 weeks or a year. Okay, but then the question is, how do we obtain a consistent estimate of beta using the partially observed data? So if A is randomly allocated and observed, both A and T are observed, then from our marginal structure model, we can write the individual partial likelihood score function. And then the average of the individual score function is an unbiased estimator of the expectation of the score function. So E of R here indicates the randomization setting. And then we can solve this unbiased estimating equation to get the consistent estimate of beta. Now, if A is still randomly allocated, but T deaths can occur before treatment initiation. So in this case, A will be censored by T. Then in this case, we can break the expectation of this individual score contribution into two parts. The first part is when A is observed. The second part is when A is not observed. Then for the second part, we can apply the law of total expectation by first conditioning on observed information and then take an expectation. So this would lead to a modification of the estimating equation. And by solving it, we can again obtain a consistent estimator. Now with the observational data, a key assumption we have to make is the ignorability assumption. And it says that the hazard function of a treatment initiation at time t is sequentially randomized in the sense that the probability of initiating treatment at time t is independent of future potential outcomes, conditioning on all covariate history up to t. So, and then we have PR and PO to denote the data distribution under randomized and non-random allocation of A. And then under both settings, we have the same set of observable data. And the observable data, if under PR is absolutely continuous with the observable data under PO, we can derive a random Nicotin derivative. So previous literature have developed a version of the Rn derivative to connect the data under the randomization setting to the data under the observational setting for the ordinary GE score. So we sort of extended for the time to event setting for the Cox score. And the reason why we wanted to do that is because then we can use it to derive some unbiased estimating equation using some weighted version of the observed data. So applying Rn derivative to Cox score is a little bit more complex than applying it to the GE score, but essentially notice that the Cox score can be represented as three averages. So the one in blue and the one in orange and the entire whole average. So essentially there are three averages, right? So each average converges to its expectation. And because it's expectation, we can do the similar tricks as we did before, break it into two parts. The second part is when we don't observe A, and then we can apply the law of total expectation. And then we apply the Rn derivative to each piece separately to construct the unbiased estimating equation. So after some derivation, we arrive at a pretty neat weighting scheme. Essentially, it suggests that for those with an observed initiation time, we're going to weight them by the marginal density function of A over the conditional density function of A. For those with A that is right censored, we're going to use second set of weight. So it's a marginal survival function over the conditional survival function. Okay, so then we can apply this weighting scheme to modify the estimating equation. And just note that we need not only weight those events, but also need to weight those individuals who are still in the risk set at a given time point. And then for censoring, we would have to make a similar assumption and using the similar techniques used for A. So the weight, time varying weight for censoring, this is for those who remain in the study by the time T. we're going to weight them by the marginal survival function over the conditional survival function. So this would lead to the final modification of the estimating equation. And censoring contributes information about our parameter estimator in two ways. The first way, when C is observed, when censoring did happen, then it contributes to the risk set up to the censoring time. When censoring did not happen, meaning that the event happened, then it contributes to the individual partial likelihood score through the weights evaluated at test time, event time. Okay, so now we know how to weight. Now back to the 4 censoring patterns. In the first case, both A and T are observed. So we're gonna weight them by the first set of weight for A and censoring weight that is evaluated at test time. Second case, A is observed, so we're gonna use first set of weight, but censoring did happen. So censoring only contributes to the risk set. Third case, A is not observed, event happened. So we're gonna use second set of weight for A, and the censoring weight is evaluated at event time T. Right? The final case, A is not observed, T is also not observed. So we're gonna use the second set of weight for A, and then censoring applies to the risk set up to time C. Okay, so that's sort of the weighting scheme for each censoring pattern. And then we know how to weight, we know what the true weights should be, but now we need to estimate the weights. So a convenient way to estimate weights is by modeling the intensity processes associated with the 2 counting process for treatment initiation and censoring. So we can, for example, fit a Cox proportional model for the 2 hazard functions, and then use the fitted hazards to estimate the denominator of the weights for treatment initiation as well as for censoring. And then for the denominator with the marginal density function, we could use the non-parametric Nelson-Anna estimator. And now we apply this method to MPAS data to solve the question of the optimal initiation time. So MPAS is the largest HIV care program based in Kenya. Our data set has nearly 5,000 patients who present with both HIV and TB. Everyone had TB therapy initiated, but their HIV initiation time, there's a lot of variability in that. Our covariates include both demographic information and disease-specific information. So some of which are time varying. Obviously, CD4 is time varying, and weight is also time varying. Others are measured at baseline. We stratify our analysis by 3 CD4 subgroups. The lowest CD4, and so the lower the CD4 count, the less healthy they are. And then between 200 and 335, they're relatively healthier. And the reason we categorize the baseline CD4 into these 3 groups is because the MPAS program has its own guidelines, which are based on these subgroups. And a few RCTs also reported results for the low CD4 group. And we wanted to compare our results to the RCT findings. So this picture shows the fitted 3 G functions from the data analysis. The first one, this is the instantaneous effect of treatment initiation, the G1 function. And this is U-shaped with the maximum benefit or lowest mortality hazard just after about 10 weeks. And after that, the longer ART initiation, the longer ART is delayed, the lower the benefit. And the second graph, that's the G2 function, that's the effect of treatment duration, essentially suggests that longer ART duration leads to lower mortality hazard. The interaction plot has an upward trend, meaning that delayed ART initiation could reduce the effect of ART duration. So, and putting that together, we can also estimate the counterfactual survival curve. So this plot summarizes the net causal effect. The top panel shows the mortality rate versus at 1 year versus ART initiation time. The bottom panel compares immediate initiation versus delayed initiation at time 8. So we can see that the benefit of early initiation is most pronounced for the lowest CD4 subgroup, and the curves are pretty flat here for the highest CD4 subgroup, meaning that there's not much benefit here for these relatively healthy patients. So a few advantages of the continuous time marginal structure model. We could further use the model outputs to emulate comparisons between regimens reported in RCTs. So for example, we could mimic random allocation of treatment initiation time by assigning a distribution for A that is independent of outcome and covariance. And then we can compare the interval-specific mortality rates and draw a causal inference about treatment initiation time. And these model outputs can also afford or provide higher resolution analysis, which may generate new insights relative to RCT findings. Just for the sake of time, I will just briefly summarize our simulation results. We considered 3 scenarios. Under the random allocation of treatment, our weighted estimators provided near zero bias and nominal coverage probability. When there's measured confounding, it sort of eliminates all of the biases and provided close to nominal coverage probability. But in the presence of unmeasured confounding, the estimates will be biased, and the bias was in proportion to the degree of unmeasured confounding. The second example is, so the second example is a dynamic treatment regimen that could still occur on the continuous time scale, but it depends on the evolving biomarker history. So it takes the form of initiate treatment when CD4 crosses a threshold value Q. And in this case, our outcome of interest is also a little bit different. This is a pediatrics data. So the mortality rate for kids are pretty low. It's less than 3 or 4%. And also, as I mentioned earlier, CD4 is an important marker of immune system function. So we're not only interested in mortality, but also interested in CD4. And both are very sparsely measured. And of course, we still have to address complications posed by the observational data. So this is a picture showing you 9 randomly chosen patients from the data. The y-axis here is the square root of CD4. X-axis here is follow-up time in days. Purple lines here, end of follow-up. 2 gray lines here represent 1 year and 2 years after the enrollment. Empty circles here mean that the patients are not on treatment yet. Solid dots mean that they're on treatments. So you can see that there's a lot of variability in the treatment initiation times. And also generally the CD4 is very sparsely measured. And there's also the follow-up times are also pretty irregular. And there's also incomplete information. Like for this patient, he or she left the study before even having the chance to initiate the treatment. And this patient, right after the treatment was initiated, either died or left the study. So also lots of incomplete information. Again, general solution is to use weighting to handle time-varying confounding. I'm going to show how we derive the closed form of the continuous time versions of the weights. And then there are missiness in the outcome, both due to sparse measurement and censoring. Strategy is to use imputation from a model of the joint distribution of CD4 and mortality. And to address the interest of in both CD4 and mortality rate, we developed a new composite outcome. Okay, so our strategy is to emulate a randomized trial in which we would randomly allocate patients to follow specific DTRs. So Q can take a value from a user supplied set. So we use Q equals 0 to denote never treat, and Q equals infinity to denote treat immediately. And then these patients will be followed for a fixed amount of time, and at a target measurement time, say T star, both the mortality status and CD4 among survivors will be ascertained. And then we will make a composite outcome, which is the product of the death indicator and the CD4. So the CDF, the cumulative distribution function of XQ, is a useful measure of treatment utility because it has a point mass at 0, corresponding to mortality rate, thereby reflecting information, both the information of both mortality and CD4 among survivors. So the probability of a positive XQ is the survival fraction. Okay, so again, we have 3 time to events and a tailoring variable events. Tailoring variable CD4, meaning that the treatment decision is made upon observing CD4 account. And then we have P/1 covariate process. So adopting a convention in the DTR literature, we assume that treatment is always made after observing the covariate and tailoring variable value. And putting everything together, for each person, we have observed a data process. And note that each person could have different time sets, discrete time sets. Then in order to estimate the comparative effects of these TTRs, we have to map the observed treatment pattern to specific DTRs. So essentially, we would need to follow 3 deterministic rules to create the mapping. The first rule says not to treat if the person has not yet initiated treatment and if CD4 has not fallen below Q or has not been observed. And if at any time T, CD4 has fallen below the threshold for the first time, treat the person. Once treated, keep treating. And then following these rules, we can create for each individual a regimen-specific compliant process. So essentially, if the rule says treat by time T and the person was treated by time T, of course, this person was compliant with DTRQ. And similarly, if the rule says not to treat and the person was not treated, then the person was also compliant. So just very simple 2 examples to illustrate how we would create the mapping. Person came in, had an initial measurement of 400, which is above the threshold 350 of our interest, the threshold of our interest. And so the rule says not to treat, and the person was not treated, compliant at this point. And this next visit, no updated or no new observation for CD4. The rule said not to treat, the person was not treated, still compliant. Next visit, CD4 down to 330, below the threshold for the first time. The rule says treat the person, and the person was treated, and so still compliant. And once treated, always treating. So the person was still treated next visit. So this person was compliant with the rule 350 throughout the follow-up. And the next example, the first 2 rows are the same. At the 3rd visit, the person's CD4 rose to 450, which was above the threshold. But on the contrary to what the rule says, the person was treated at this time. So then from this time onward, the person was not compliant with Rule 350. Okay, so then we can follow in these rules to create for each person in the data a compliance, regimen compliance process. And then general imputation techniques for missing data. For those who had a missing data, for those who are alive but have a missing data because of sparse measurement, we're gonna impute the missing CD4 from the fitted CD4 submodel. For those who have a missing outcome because of right censoring, we're gonna first impute a death indicator from the survival submodel. And then if the death indicator was imputed to be 0, then we're gonna further impute a CD4 count from the CD4 submodel. Otherwise, we're gonna set the outcome to be 0. And then now to estimate the effect of DTRs, we could estimate the effect of discrete DTRs. We could also propose a marginal structure model to capture the smoothed effect of Q on the tallest quantile of XQ. So our proposed structure model could capture the separate effect of treat immediately and never treat, everything in between the smoothed effect. So we could again parameterize the model using splines of Q for this part. And then we would have to obtain a consistent estimate of effect of Q by solving the weighted quantile regression estimating equation. What should be the weights? Visits are not nicely aligned. Censoring happened all over the place. For the discrete time setting with common times, this work has been done. Essentially, it's been shown that the denominator of the weight should be the conditional probability of being compliant with a specific rule, conditioning on all covariate history up to T star. And it's essentially the cumulative product of being compliant at every discrete time point. So this suggests that we just need to model the observed treatment initiation process among those regimen compliers to estimate the denominator of the weights. But what about the continuous time? So the continuous time, we can observe that the occurrence of treatment initiation in a small time interval is actually a Balloony trial with outcome DNA of T. Then we can rewrite this cumulative product in terms of the individual partial likelihood score for the counting process of A. And now we observe that when dt becomes smaller and smaller, this finite product approaches a product integral. And then, so this can be written as the finite product over jump times of the counting process times the survival function. And then by further recognizing that each person has at most one jump at exactly time AI, we could further reduce this product into this formula, which suggests the weighting scheme. For those who have initiated treatment by T star, we're going to use the inverse of conditional density function, conditional density function. For those who have not initiated, we're going to use the inverse of survival function. So, right. So if you recall the weighting scheme that was derived by the random Nikodym derivative from the previous example, this weighting scheme is actually in accordance to that, with that. So we took a different approaches, but arrive at the same conclusion. So still similar strategies, we could use a Cox regression model to estimate the hazard functions for the treatment initiation process, and then estimate the denominators of the weights. And then we can use the non-parametric estimator to stabilize, for the numerator, to stabilize the weights. And then we apply the methods to analyze nearly 2,000 patients drawn from the East Africa IDEA Consortium to estimate the comparative effects of CD4-based DTRs. We can see that the CD4 counts is CD4 is very sparsely measured, and the mortality death rate is also pretty low. For time varying or for covariates, some of which are time varying, obviously CD4, and weight for age z-scores, height for age z-scores, some of them are time fixed. So we're interested in, of course, mortality proportion, and we're also interested in median value of the composite outcome. We also look at the CD4 among survivors, but note that this is not a causal effect because it conditions on having survived to time t. But so this theta Q3 is not causal effect, but theta Q1, theta Q2, these two are causal effects. Okay, so this table summarizes the comparative effect of 5 specific regimens. We can see that treat immediately would lead to significantly lower mortality rate compared to delayed treatment and significantly higher median values of CD4. Never treat regimen would lead to significantly higher mortality rate. And CD4 among survivors are relatively higher, so driving up theta Q2 and theta Q3, which may suggest that those without treatment who do survive to 1 year or 2 years may be relatively healthy at the beginning of the follow-up. We can also plot the dose response curve for the median value of XQ versus threshold, which gives us a same message. Treat immediately would lead to significantly higher median value of the composite outcome at both years compared to delayed treatment. And by modeling the smooth effect of Q on the outcome, we also compare to the estimates of the discrete regimen, we gain a bit of efficiency. So to summarize, the strength of continuous time based marginal structure model, there is a closed form of weights. We can handle complex data set on its own terms without having artificially aligning measurement times. This model, this marginal structure model, is amenable to different outcome types, whether continuous binary, survival, or composite outcomes. And it can handle data complications introduced by censoring within the same model. And of course, it also has limitations which open up opportunities for future research. Immediate next step could be, I'm not sure if this is worthwhile though, to derive the asymptotic variance by using martingale residuals to form an empirical estimator. We could do better in terms of addressing extreme weights. So for example, instead of the Cox proportional model, we could use machine learning that can account for time varying confounding to estimate the weights. We could do adaptive training perhaps to sacrifice a bit of bias to gain efficiency, to gain stability. There's also there's also literature on optimal weights. It's a similar idea, sacrifice a bit of a bias for a variance trade-off. We could also gain a bit of efficiency by using knowledge from the outcome-based modeling. So it is known that weighting-based method is less efficient than the so-called G computation or G estimation. But for longitudinal data with time-varying confounding, both the G methods require integrating over the space of longitudinal confounders. So computationally very intensive. As far as I am concerned, there's no continuous time version of the G computation method. I know Judith Locke developed the theory for continuous time G estimation method, but just haven't seen a practical implementation of that method. So how to borrow in the strengths of outcome modeling perhaps to form a doubly robust estimator. That's an additional topic for future research, because the marginal structure model, that's the Cox proportional hazard. That's also complex, because hazard, that's a ratio that's non-additive. So that's another complexity that sort of impedes forming a doubly robust estimator. So that's a future, that's the topics for future research. And these are sort of key references for these projects. And we're still working on some of the projects right now. And thank you so much. And if you have any questions or suggestions or comments, feel free to let me know. Thank you.
Thank you so much. I see a lot of clapping reacts in the.
I see that.
So I think we have time for 1 or 2 questions. If anyone wants to either throw it in the chat or just unmute yourself.
I can ask a question. So you've done such a beautiful job of creating a really principled and thoughtful approach to situations where you've got multiple things going on at once, the continuous time, the censoring and all, right? It's a super hard problem. What would people have done with this problem in the absence of what you've created? Like, what are the hacks that people would have been using?
Right. And for immediate, so when we first work on the problem, because clinicians are interested in estimating the causal effect of actual timing. But in the existing literature, people always categorize, like binning. So they would categorize initiation time into several intervals. So literature did exist comparing the effects of initiating within 4 weeks of TB therapy, between 4 weeks and 8 weeks of TB therapy. That's it, comparing two initiating intervals. So this is the problem. It evidently would lead to loss of information. We have a great variability in terms of the treatment initiation time. And also there are people, and this would also create opportunity, I guess, for implementing the so-called G computation methods, because it does require, the aligning of the follow-up times for the G methods. So this is actually the first work that we would say, hey, let's not bin, let's just evaluate the effect of the actual treatment initiation time. So that's why we took this approach to consider the continuous time-based marginal structure model. But then, yes, we addressed it's good, and it's versatile to address a lot of complications. But also the weights could be a bit of unstable because it's density function. And so that opens up, as I said, the limitations of this approach. That opens up research opportunities. So how do we stabilize the continuous time weights, continuous time varying weights? That's an important question. And we also thought about using G computations, but I'm not sure. I haven't found any literature in this area, like using outcome modeling based approach, but without having to bin the times, just to use the continuous time scale. It's just I think it's very hard. I'm not sure if it's possible to derive a closed form of G computation formula, but I haven't seen any literature on sort of continuous time G computation or G estimation methods. So it's pretty hard problem if we don't want to bin the time.
Well, congratulations for taking it on. Do other people have questions?
Thank you.
If not, let's thank Liangyuan again for such a great talk. And to everyone in the audience, we look forward to seeing you at our next PRIISM seminars. Thank you so much for coming.
Thank you so much for having me.
Thank you.